about ionization. Ionization is just where things break apart. In this case, weak acid is breaking apart to form a proton, and the rest of the weak acid. Okay, it's in equilibrium. So we're going to kind of just keep moving on with this theme of, we're going to focus on weak acids, not strong acids, weak acids. We're going to focus on, we're just jump in and do some problems. So if you're working this problem on a test and it says niacin, you're like, I have no idea what niacin is a weak acid. You're like, but I do know what weak acids are. And they give you a formula like this. Now, if they say it's a weak acid, you should be thinking, oh, I bet it kicks off a proton. I bet it kicks off a proton. I bet it kicks off an H. So hopefully you're thinking, I bet that's the one that goes. And you would be right. The C6H4, am I thinking this right? Anyway, that's kind of embedded, but that's the one that's going to go. It goes ahead and it gives you the molarity of the weak acid. Now, in a minute, on the next slide, you're going to say one of the things you should be doing is taking the weak acid and showing the equilibrium like you're doing for the homework, I think, that you're handing in. Okay, so we're going to do that. It gives us the pH of the solution. So you're like, pH, one of the things I know to do about pH is I can get that hydrogen ion concentration. And actually, that's what we're going to do. That pH, we're going to go for the hydrogen ion concentration. And they want to know what the value for Ka is. And you're like, I have no idea. Well, let's just see what we got. We actually did this sort of problem before, similar. You were given the initial concentrations of everything, and you're given the equilibrium concentration. I'll put a little subscript E here, my H+. You're given the equilibrium concentration of one of the species. That's my subscript E. Okay, and we can come up with equilibrium concentrations of everything, plug them into Ka expression, and come up with the answer. So like I said, when I grade this, or when you work this, this is where you start. You cannot work this problem otherwise. You write the Ka expression of the weak acid ionizing. You see where the H+ kicked off. You can kind of see on the product side where that went. So for weak acids, we write the Ka expression. Okay, it used to be a Kc expression or K expression, equilibrium constant expression. It looks like this. Your equilibrium constant expressions, including your Kas, are always going to be products over reactants, raised to the stoichiometric coefficients. Okay, the molar concentrations of everything is one across the board. And we don't have Ka, we're supposed to calculate Ka. Now, for this semester, I actually inserted, I hope it works out okay, I inserted an ice table. You wouldn't have to use an ice table, but I like it for organizing things and see what we think. So somewhere in your notes, I don't know if you're going to have room to put these extra slides I have. So here's an extra slide I have. So if we let X be equal to the amount of the niacin that ionizes, I'm going to put an X here. Okay, and the stoichiometry is one across the board. Don't let stoichiometry throw you off. But that means that this is the amount of H+ that's going to form or be released, and that's also the amount of that C6H4NO2 negative. That's actually what we call the conjugate base of the niacin. So with that in mind, here's what my ice table looks like. Again, you guys don't have this slide, so if you need to write on the back of something or just soak it in, it can be worked without an ice table too. But one thing to know about ice tables is we make the columns. So my first column is my H, molarity of my weak acid, HC6H4NO2, then the molarity of my H+, and then the molarity of my C6H4NO2 negative. So of course we have initial change and at equilibrium. So for this sort of problem, the only thing we know, or the only thing we have initially, is the molarity, basically no pun intended, the weak acid before it hydrolyzes, before it breaks apart. None of this, guys. So the change is going to be negative x, and plus x. I hope that makes sense. We're going to let it rip, and certain amount of your nicene, your C6H4NO2, is going to break apart and give you, whatever breaks apart is going to give you equal molar amounts of H plus and the conjugate base over there. So then we know to get at equilibrium, you take the initial and apply the change. So at equilibrium, the molar concentration of your weak acid is 0.012 minus X. The molar concentration of H plus is X. The molar concentration of that C6H4NO2 negative is also X. And here's the catch, and you're going to see this here in a minute. We know the pH. So I can get X from the pH. And if I get X from the pH, I can start filling in all these X's. All right. So this goes back to, you should have this slide. You already have this slide. So this is part of what I ended up putting on an ice table. So initially, that's what the little 0 means. Your initial molar concentration of your nicene is 0.012 molar. Initial concentration of H plus ion is essentially 0. Now I'm going to have to go back and have a slide to explain that. In water, it's not really 0, right? You have some auto-ionization, so you have a certain amount of H plus there. It really doesn't make a difference. And your conjugate base is 0. So like I was saying, and I like the ice table because it kind of organizes things. At equilibrium, we were given the pH, so we know the hydrogen ion concentration. To get to the hydrogen ion concentration, we take 10 raised to the negative pH. So in this case, it's 10 raised to the negative 3.39, which if you plop that into your calculator, you get a molar concentration of hydrogen ion 4.1 times 10 to the minus 4th moles per liter.
Where did you get the negative 3.39?
It was in the problem. That was the
sorry.
pH. You're fine. That was the pH in the problem.
Okay.
Mm-hmm. Yep. So now if you're using an ice table, you can kind of go back, and that's your X. So actually, I have this statement we're going to work 2 problems in this part, and I make this statement twice. Back on our ice table, when we said initial molar concentration of H plus is 0, is that true? Mm-mm. We know that actually water auto-ionizes at 25 degrees Celsius. To give you your Kw of 1 times 10 minus 14, square root of that is 1 times 10 minus 7. So that's what normal water is running with regard to the hydrogen ion. But as it works out though, if you were to put 1 times 10 minus 7 in your ice table, it still wouldn't have made a difference in your result. Okay, so this is what our ice table looked like. And like I said, and you don't have to jot this down, this is what you already have. And wherever there's an X, I can go ahead and plug in 4.1 times 10 to the minus 4. So this is what that looks like, kind of coming full circle. The first thing I know about is the equilibrium concentration of your H plus. So that means that I'm adding 4.1 times 10 minus 4. So now X over here for the change in the molar concentration of your C6H4NO2 is also plus 4.1 times 10 minus 4. You add that to 0 and you get 4.1 times 10 minus 4. Over here now, with our weak acid, we had an initial molar concentration of 0.012. Apply the change of 4.1 times 10 to the minus 4th, that will be negative. And as this turns out, since we're subtracting, we have to round according to decimals. And actually, there is no impact on applying a change. So that's why at equilibrium, the molar concentration of your weak acid is still 0.012 molar. By the time you round like you're supposed to. So what we did with this sort of problem before to knock out a Kc, in this case a Ka, is we just substitute these back into your Ka expression, and that will give us our Ka. And you guys have this this slide. I just didn't like, I like the ice table better. So you guys should already have this slide.
Okay, I thought it's 70, so
Okay.
knock it down. Okay.
So from stoichiometry, at equilibrium, that's your conjugate base, that was your third column, equilibrium concentration of the acid that lost a proton, C6H4NO2, will equal to 4.1 times 10 to the minus 4th. So it's basically the same thing without the ice table. Very good. All right. So last but not least then, we go back to our equilibrium constant expression, our Ka expression, where we had the molar concentrations of the two products divided by the molar concentration of the reactant. Plugging in real numbers then, it looks like this. Ka is equal to 4.1 times 10 to the minus 4th times itself squared, divided by 0.012. That was the molar concentration of your weak acid. Giving yourselves 2 sig figs, I get a Ka of 1.4 times 10 to the minus 5th. So again, we got the Ka from the initial molar concentration of your weak acid, and at equilibrium, the pH. Counting slides. Yeah. And Rhonda is verifying.
Yes. I like this calculator better.
Good. Okay. So one of the realities of working chemistry problems is it takes a minute to soak it in. What sort of problem do you have? What direction should you go? Again, I feel for you. The more problems you do, the more you'll know what to do. Now this one's slightly different. We're given the Ka, and we're supposed to knock out the hydrogen ion concentration and the pH. Well, if you got the hydrogen ion concentration, you're just that close to knocking out the pH. Well, but it goes back to what I said for the first problem. By golly, what you're going to see me do on the slides is I'm going to take that acetic acid, CH3COOH, and I am going to show it ionizing. And hopefully you're good with this. So I need to show a proton kicking off. I need to show an H going away. It's not going to be one of those. It's going to be this guy right here that goes away. I mean, it doesn't make sense to take one from the carbon. It's going to be the one off the oxygen that goes away. Okay, so we could write, and we should write, the equilibrium, this is the equilibrium of the weak acid ionizing or breaking apart. Here's the proton that's kicking off the end, and here's what's left. What's left is going to be -1, and of course the proton is a +1. We could write the Ka expression, and it would look like this. So Ka is equal to the molar concentration of H plus, also in the numerator, the molar concentration of CH3COO negative 1. In the denominator, it's the molar concentration of the weak acid. The denominator is molar concentration of CH3COOH. And the Ka this time was given 1.8 times 10 to the minus 5th. Again, what are we after? We're after the molar concentration of the hydrogen ion at equilibrium. Well, you can't go wrong setting up an ice table. Actually, you should have this already, right? So if we set up an ice table, it looks like this. We have 3 columns, one for your CH3COOH, one column for your H plus, and one column for CH3COO negative 1. So what would be the change then? What do you think? What's the change of the CH3COOH if we let X be equal to the amount of CH3COOH that ionizes? Is it plus X or minus X?
Minus X.
I'm liking it. How about this guy over here?
Plus.
It's plus X. Perfect. What about this guy right here?
Plus.
Also plus X. All right. So we take the change, we take the initial, apply the change, and get equilibrium concentrations. You guys got this. So at equilibrium, for the CH3COOH, you're looking at 0.10 minus X. The H plus, you're looking at X. And for the CH3COO minus, you're also looking at X. All right. Now, this might give you not necessarily warm fuzzies, because if I take these 3 quantities, plug them back into my Ka expression, equal to a Ka that I know, now I have to solve for X, and that's like very ugly. You're going to need to invoke what we call another simplifying assumption. So here we go. Oh, before I do that, this is the same statement I had before. Under H plus, it says 0 initially. You're like, I don't think that's quite right. You know, at 25 degrees Celsius, I should be running about 1 times 10 to the minus 7th moles per liter. But that's not going to make a difference. Okay, here we go. So this is what it looks like. This is what I described a minute ago. So you're like, all right, so I got basically x squared over 0.10 minus x is equal to 1.8 times 10 to the minus 5th. I can use the quadratic equation. I can use something online to solve for x. But we are going to apply a simplifying assumption. Did you know what the word assumption? Have you ever heard this before? You should never make assumptions because this, I didn't make this out. It makes, you know what? It makes an ass out of you and me. Assumptions. I know. Anyway. Okay. Here we go. This simplifying assumption, and it's going to feel familiar to what we did with the insoluble salts. We said the amount of salt that dissolves is pretty much negligible. In this case, we're going to say that the amount of acid that ionizes, the X, is pretty darn small. That's double less than, pretty darn small is the technical word for that. Pretty much less than the initial molar concentration of the acid, which was 0.10. If that's the case, then basically that's very small. So that means that this term right here, 0.10 minus x, x is so small that that term becomes 0.10. And it makes life a lot easier. So now we're going to go ahead and substitute in 0.10 instead of 0.10 minus x. The rule of thumb is if your initial concentration, this is a weak acid, initial concentration of your weak acid, I'll put WA there. In this case, the molar concentration is 0.10. This is weak acid. If it's less than 100 times Ka, so how that would go was we would take the Ka times 100, and for this case, I get what, 1.8 times 10 to the negative third? So if your molar concentration of weak acid, which was what, 0.10 here, if it's less than 1.8 times 10 to the negative third, it's a pretty good assumption. And it is. Okay. So let's see what that looks like then. Yep, life just became easier. Now our equation looks like this. X squared over 0.10 is equal to 1.8 times 10 minus fifth. And however you do that, you end up with getting, you take x is equal to the square root of 1.8 times 10 to the minus sixth. And then allowing yourself 2 sig figs, x is equal to 0.0013 moles per liter. And if we go back to our ice table, x, then we can pick off the hydrogen ion concentration. That is the hydrogen ion concentration. So that's the first of 2 questions. And then, of course, a follow-up question is, what is the pH? So once we have the hydrogen ion concentration, we just have to take negative log of 0.0013. Oh, down there in green, it's a little PS. It was, if you were to go ahead and apply the quadratic equation to get an exact solution instead of applying a simplifying assumption, you could also get the same number in this case. Okay. So like I said, to get the pH is equal to negative log of 0.0013. And remember how that works. I have 2 sig figs here, and I show 2 sig figs by the digits after the decimal. So it's like this. 2.87. So those are 2 types of solving equilibria for weak acids. You're funny. Okay. So this part will be due. I'm catching up with how far I've gotten. I think I have to do homework for part 5, I think. I think I've got 4 posted. Do I have 4 posted? Do you have 4 parts posted?
So was the final answer 2.88? Because 2 significant figures?
I got 2.87. Oh, yeah.
So we'll round up with it, or no? Because I got 2.886. That would round up to 2.9.
2.89.
Yeah.
I don't know.
Okay. Well, it's such a smidge off, right?
Yeah,
if I show everything,
yeah,
then there's no problem.
Yeah. I don't know. I wonder if I used an unrounded value. Inquiring one. She got 2.89.
Log. Oh, it's just regular log, right? It's log times.
Yeah.
We have to do the negative.
Yeah, I did too.
Oh, okay.
It's the 10th is assumed if you don't put it down.
Yep.
So yeah.
2.86.
I don't know if I used an unrounded value. So thank you. So I'm going to put a question mark 2.89. Very good. Okay. But yeah, and when I'm grading papers, sometimes I'll come the whole smidgen thing. I'll be like, oh, that's pretty close, and their work looks good. So in this case, it looks like I made a mistake. All right. We could do this one. This one's short. Even shorter, I think. Is it even shorter?
It's like 2 pages.
Yeah. Sorry, guys. All right. And actually, the first slide we've already had before. This is like a deja vu slide. Monoprotic means it picks up only one proton. A proton's a H+. Polyprotic means that you have an opportunity to pick up more than one proton. And amphiprotic means it can either accept a proton or donate a proton. And remember, water is a great amphiprotic substance. There are a lot of things out there that can either pick up one more hydrogen or bring in a hydrogen. So if you're dealing with the polyprotic acid, this almost intuitively sounds right to me. The first one will kick off really easy. The first H+. The second H+, not so much. Okay. So the Ka for the first ionization will be greater than the Ka for the second ionization. So and we are going to evaluate an example. I think we're going to look at sulfuric acid, H2SO4. What we're going to see is that basically the pH of an H2SO4 solution is mostly driven by kicking off that first proton, because kicking off that second proton doesn't do it to nearly as much of an extent. So here we go, sulfuric acid, H2SO4. So we're supposed to come up with the pH of a 0.10 molar solution of sulfuric acid. And we're going to break it out into parts. So we're going to consider the molar concentration of the hydrogen ion that's brought by the first kickoff to form HSO4-, and then the second kickoff when HSO4- goes to form SO4 2-. And I'll show you what this looks like. So now one-way arrow, hopefully, and I ran into this with my other chemistry class today, a one-way arrow means no equilibrium, strong acid. There were 6 strong acids to memorize, sulfuric acid is one of them. So the Ka is just simply very large. Notice it's the Ka1, because I'm going to have a Ka2 here in a minute. What can happen then is the bisulfate, SO4-1, it can go ahead now and kick off a proton, but now it's in equilibrium. It's not a one-way, it's not strong. This is a weak acid. It kicks off one more proton, and it forms the SO4 2-. Still pretty high Ka. So the Ka2, the ionization constant associated with this step is 0.012. Okay, so from the first ionization, we can assume that the molar concentration of the H+ is 0.10. This is what I mean. So like over here, 0.10, one-way arrow means I have 0.10 and 0.10, right? Makes sense. So in this problem, I'm basically going to, that's kind of my starting point. That's for the first ionization. Oh, while we're at it, check this out. I'm going to go ahead and take this 1.10, and it's going to be the initial concentration of what's going to be weak acid. Does that make sense? Now, I'm going to try to get the molar concentrations. I'll stop there, but we'll back it up. Okay. So now in this case, a minute ago on that first one-way chemical reaction, I told you we're going to get 0.10 molar H+ from our first ionization. We can't blow that off now. We kind of blew it off before, but it's significant in the equilibrium of the HSO4-. Okay? So we're going to end up making an ice table. So this is the ice table for the second ionization. I'll put a number 2 up here. This is the second ionization. So hopefully you saw where that came from. Remember? 0.10 molar was from the initial, the first step. And then we have 0.10 moles per liter is a common ion now in that second equilibrium. It's the only equilibrium, second ionization. Don't have any sulfate there. we go ahead and with this second ionization we're looking at, we're going to let X be equal to the amount of molar concentration of HSO4 that ionizes. And so it's going to be a negative X. We're going to have a plus X for our hydrogen ion and a plus X for our sulfate ion. And then, of course, at equilibrium, we take the initial, apply the change. Take the initial, apply the change, take the initial, initial change. So what we know then to get the X is, remember we were given the Ka2 of 0.012? Okay, we could take these quantities, plug them back in, and solve for, use our quadratic. I think it might be more a higher polynomial than 2, I think. But anyway, but we're not going to do that. We are going to apply a simplifying assumption. Sorry, I put two things out there. The first one is plopping back into the Ka2 expression. So in the numerator, you're going to have the molar concentration of hydrogen ion, 0.10 plus X, molar concentration of SO4 2 minus X. Down the bottom, you're going to have the molar concentration of your HSO4 minus, 0.10 minus X. That's equal to your Ka2. So the simplifying assumption we used last time, we're going to do it again. We're going to say, I bet X is pretty small compared to the initial molar concentration of that HSO4 minus. So we bet that X is pretty darn small compared to 0.10. If that's the case, then our two quantities, which is unusual, it's a little different than last time. If that's the case, then two of these quantities become simpler. If you have 0.10 plus not much, you get 0.10. If you have 0.10 minus not much, you get 0.10. So it's going to look kind of weird. So plugging in now, it looks like, are we all on the same page here? I'll do it up here. So this quantity went to 0.10, and this quantity, the whole quantity, went to 0.10. So actually 0.10's cancel, and I have X is equal to 0.012.
Isn't that weird? Oh, okay. It's actually, I mean, it's not
it's
like
the
a negative
Ka2.
1 or anything.
What's that?
It's not a negative 1 or anything, because there's a negative and a positive. It's just plain old. Okay.
Yep. So that would be, by definition, the hydrogen ion that was donated with our second ionization. So let's check out our borderline. Let's check out, I'm going to go back to this slide, if that's okay with you, and think through it. Remember we said that this works if, what did we say? The molar concentration of your weak acid is less than your Ka times 100. Okay, so this is our Ka2. So Ka times 100 is, wow, is it 1.2? Right? And the molar concentration of our HB was 0.10. So the question is 0.10 less than 1.2? Yeah. But is 0.10 much less than 1.2? No. That's why in the next slide, this is actually a borderline situation. Do you know what I'm saying? Should be greater than. Let's see, what's that? Wait a minute.
It's less than.
Yeah. Oh, if the. Yeah, this is if it. Drat. Oh, it's in the previous one. What did I'll look over somebody's shoulder. Somebody pull up for the previous part. And I think I told you wrong. This is supposed to be greater than.
Point 01 is greater than 1.2?
Yeah, on page 3, the top slide of page 3. Oh. Okay. Yeah. Because, yeah. Sorry. This guy right here,
Yeah.
this should be a greater than.
Oh.
Yep.
Because the numbers don't.
Yeah.
They look right. Okay.
Yeah. So then we end up with, is 0.10 greater than 1.2?
And KA, does that is less than 100 or is it greater than
It's
100?
KA times 100.
Oh, times.
Times 100.
Oh, well, very fast.
Yeah, so anyway, it fails the test. This is a general test, and it failed. Because your Ka was pretty high, and your concentration wasn't all that high. Does that make sense? Okay, final answer. And actually, that's what this slide says. It says that our simplifying assumption, I wouldn't even say borderline, I'd say it fails the test. And so instead of 0.0012, instead of 0.012, if you were to solve for x, instead of applying simplifying assumption, you're going to get 0.0098. So it is different. You know what I'm saying? Say versus 0.012. And this is the better answer because it's without the simplifying assumption. Who wants to figure out quadratic? So to finish this problem, actually, I'm going to use this better molar concentration of hydrogen ion. Okay? So this was actually the molar concentration of hydrogen ion that came from the second ionization process. Okay? All right. Okay. So here we go. Let's see what we got. From the first ionization, strong acid, we got this. From the second ionization, using an exact solution quadratic equation, you're looking at the hydrogen ion 0.0098 moles per liter. And let's see. We can add those two, and your calculator is going to spit back 0.1098, right? And we know if you're adding things like this, you have to round according to decimals. We can only have 2 decimals. Okay? So actually that 0 is going to round up to 1. Bottom line, when you add the 2 together and you round it right, you're going to end up with 0.11 molar hydrogen ion.
Could you look and see if I did something wrong here?
Because of the
So
pink,
it's,
I'm
I think it's adding, not subtracting.
Oh,
Yep.
duh. Alrighty.
Yeah, the pink's kind of. So that's it.
That was pure me.
So we could knock out a pH then, with and without the effect of that second ionization, and here's what it will look like. So the pH with the second ionization would be a negative log of quantity 0.11. So you're looking at 0.96 as your pH. And if you compare that to, so this is with both ionizations. If you compare that to just the first ionization, the pH would be equal to negative log base 10 of 0.10. That was the first. And in that case, you'll get a pH of 1.00. So down here at the bottom, that's exactly what it says. It says, well, okay, what if we don't consider the second ionization for sulfuric acid? What's the pH of a 0.1 molar solution? And it would be pH of negative log of 0.10, which is 1.0. So, now one of the things about the pH scale, remember, is that it's log base 10, so each unit is 10 times. Two more slides. Okay, cool. So back to the definition of amphiprotic, okay? HSO4, the bisulfate ion it could go either way, because it could accept a proton, but that's not likely because it's going to form a strong acid, or it could donate a proton. If it accepts a proton, it's behaving as a base. If it donates a proton, it's behaving as an acid. And when it comes to amphiprotic substances that can go either way, it kind of depends on what else is in their soup to which way they're going to go. What's the most common amphiprotic substance? Water. Donate a proton, become a hydroxide, leave hydroxide, or can pick up a proton and become the hydronium ion. So let's start part 5. Just kidding. Very good.
You know, it slipped up in my head was that when you had said that you